So far we consider two types of tests, okay, right tail test and lower tail test. It would be interesting to look at two tail tests. Okay, so this is the one example of the two tail test. Okay, so in this example, a medical rehabilitation education foundation reports that the average cost of rehabilitation for stroke victim is 24.70, okay, not point, but 24,652. To see if the average cost of the rehabilitation is different at a particular hospital, a researcher selects a sample, a random sample of 35 stroke victims at the hospital and find that the average cost of their rehabilitation cost is 26,343. And the standard deviation for the population is this one, and at this level we can conclude that the average cost of the stroke rehabilitation at a particular hospital is different from this value. Okay, so we want to know if the cost of the average cost of stroke rehabilitation at a certain hospital is different from this value. This is a specific value. And we want to test that the average cost of stroke rehabilitation at this certain hospital, whether they are different from this. So in this case, you can state the hypothesis and identify the claim. So this is the initial value, right? And you want to test whether they are different or not, right? So then in this case, different can be greater or less than. That's why you come up with the different. It is in this case a two-tailed test, right? This is your claim, and based on the sample from the certified stroke victims, it support our claim or not, right? Okay, so we want it to be 0.01 significant level. So with this significant level, we have to find the critical value, and then we end up with these two values. Why? Because it is two-tailed test. So later on, we have to compute the test value. Okay. So in the sample mean is given, sample mean here. Okay, based on these 35 victims, we found that on average they spend this amount. That's why this is the sample mean. And then the population standard deviation is this one. I mean the sigma. And the initial claim is this. Then you end up with a test value of 3.04. 3.04 is between these two values. So just like inside the non-critical region, right? Because for the two-tailed test, there are two parts of the rejection region. The value which is less than this one or greater than this one. I'm sorry, it's greater than this in the rejection region. So this value fall in the rejection region, so we have to reject the null hypothesis, right? Yes. here this is a rejection region. We have two parts: the value less than this value and the value greater than this. And we found our test value to be 3.04, which is inside this part of the rejection region. That's why when our test value is inside the rejection region, we have to reject. Okay. So how to reject? Okay. Summarize, there is enough evidence to support the claim. You reject this null hypothesis, it means that you support H0, which is the claim, right? The claim. The claim is the alternative hypothesis. And once you reject it, it means you support the claim, right? Okay, so there's enough evidence to support the claim that the average cost of rehabilitation at a particular hospital is different from its value. I mean that we support this. Again, this support just from the sample you collected, right? But it may not true that the claim is correct, right? Because there some error may happen. Right? Okay, here here is the code, right? Here is the code for the first example. Okay, the code for the first example, which is this one, right? This one. I just summarize all the amount related to this one, and then I can come up with this R code, right? So you have to specify the alpha to be 0.10, and the initial value of the population mean is this value, and from the sample you come up with the sample mean to be this, and the standard population standard deviation is known, okay, to be this, and you choose a sample of size 36, and then this is the formula for the critical value. Okay, I'm sorry, not critical. The test value, and then this is the critical value C alpha, right? C alpha. You can get C alpha from this. Okay, I already explained you. Okay, already here. So this is how to decide on your conclusion. Depend on the Z value you computed from the sample, right? So you may look at this conditional in R programming. Instead that if Z value is less than the critical value, this means that Z is inside the rejection region, right? Because this is the left tail test. I remember from the first example. So if Z is in the less than the critical value, it means that it falls inside the rejection region. Then your conclusion is to reject the null hypothesis. Reject null. Else mean if Z is greater than Z alpha. Else print there's not enough evidence to reject the null hypothesis. This is the code for the left tail test, right? So I already have it here. Okay, here I have it here. Okay, this is alpha x bar, and I just list down everything, and this is the conditional code that. Okay, so once everything is input, so I have to run this code. Okay, I just select all and then control enter, and then I will come up with this result. The result is not to reject the null hypothesis, right? The result is not to reject the null hypothesis. And we also found this same thing. There's not enough evidence to support the claim. Oh, no, not this example. Oh. Okay, I guess this is okay, this is a second example, 7, right? We end up with there is not enough evidence to support the claim. It means that we have to do not reject H0, right? Do not reject. And by R, we found that we do not reject the null hypothesis. Just come up with the same result. So this is how you do it hand by hand, right? Manually. But once you want to use the R, just run this code, and it's just a piece of cake. Just enter the numerical value and then just give it. So it seems that calculation doesn't matter, because now you have a very wonderful statistical software to assist you in numerical calculation. But the thing is that you have to know how to interpret the result, right? Okay, you know how to interpret the result. Okay, that is the main thing. Originally, when the computer science is not that good, people just use hand and come up with a very complicated calculation. But now we have very good computer software that can assist us on that matter, but still we have to know how to interpret the result generated by the computer. Okay, you may ask, okay, it sounds that we have to write very complicated code. Okay, because R is free, and then the code can be write by using a series of commands, different from the SPSS that you have to put only the number and then we generate you very nice result. But as I said, it's not free, right? SPSS, and sometimes it's not flexible. In R, you can write any code to reflect the real situation you want. And even here in Excel, actually Excel, there's no hypothesis testing for a single sample, right? Just like our example. You have to download the add-in name Megastat, which is not free in this case. So in order to use Excel, you have to install this add-ins named Megastat, and I searched that it's not free, so you have to pay to come up with this value. But usually it gives a different the code, the software just give you a different calculation, which will be considered later. Okay, so I think we should stop here from the first section. Okay, so so far you see that once you carry out a hypothesis testing, you have to decide on the significant label, right? The alpha. So it could be 0.05, 0.01, or sometimes just 0.1. So this is nothing but the seriousness of the type 1 error, right? Because the significant label alpha is nothing but the probability of the type 1 error code. So it depends on you how you serious with the type 1 errors. If you choose alpha to be very small, 0.01, it means that you want the type 1 error to be occur at only 1% of the chance, right? And so far, when you decide on the confidence, the significant level, you have to compute the critical value, right? And you have to base on the critical value to decide whether to reject the null hypothesis. But in some statistical software, it will not give you the critical value, but instead it gives you the p-value. Okay, it's another value that help you to decide whether the null hypothesis should be rejected. Originally, we see that we based on the critical value, and now we are based on the p-value. So what is p-value in this case? Okay, p-value is the probability value. Okay, it's the probability value, and what kind of probability it is? It is the probability of getting the sample statistic. Okay, in the direction of the alternative hypothesis HA or H1 when the null hypothesis H0 is true. Basically, if you look at this example, if you look at this example, this is the, in this case, your significant level is 0.05, and you found that the critical value is 1.65. It means the point that corresponds to the area to the right under the curve is 0.05, right? And your test value in this example is 3.39. So the p-test, okay, the one I just mentioned a while ago, the p-test is nothing but this area. Okay, the area under the curve to the right of this test value. This is mean the p-test. So instead of comparing the test value with the critical value, you will compare the p-value, which is this area. You have to compare this to the significant level, the alpha. So again, if you look at the critical value and the test value, you will see that the test value is fall inside the rejection region, or in other words, it is greater than the critical value. So you have to reject the null hypothesis. But in the same case, you may just look at the area. Okay, this area corresponds to this test value is smaller than the critical, the significant level. So you also reject the null hypothesis. So nothing, p-value is the the area under the curve correspond to the test value. Right? So if you look at the definition by word, maybe it's a little bit complicated to understand. But as I said, this is how we define P, right? P value. P value is the probability that okay, a while ago we look at the right tail test. Okay? The right tail test. The P value is the probability that the test value, okay, greater, the test statistic greater than the test value. Right? I mean the area correspond to the test value. Okay, by knowing that the null hypothesis is true. Okay, for the left tail test, we define in a corresponding way. Okay, for the left tail test, your p test in this case is this area, right? This area. And for the two tail test, you have to define P in a different way. You have to count the area under the curve at the test value and the area under the curve at the negative of the test value. I mean, here our test value is 3.04, so its negative is negative 3.04. So the p-value in this case is this small area at another small area here, right, which correspond to the sign of the test value. That's why you see the definition is one, the test is two tail. You will see that it involves the absolute value, right? That is how it means by it. Here, TS refer to the test statistic. So far, our test statistic is the Z, right? The Z test, the Z distribution. So, how to decide based on the p-value? Okay, as I said, you have to reject the x0 if p-value is less than the significant level. Right? Otherwise, you do not reject the x0. Just like I explained a while ago, this is how you can reject or not reject the x0, depend on the p-value. Why we need p-value? Because the code I give you a while ago doesn't involve with p-value, but only the critical value. You have to compare the test value with the critical value to decide whether to reject or do not reject the null hypothesis. We need p-value because mostly in statistical software, it will print out the p-value. Okay. So for example, here we run by Excel. Okay. As I said, the Excel, Microsoft Excel do not provide you the statistical tool for hypothesis testing of a single sample. You have to install this add-ins called MegaStat, so that you can use Microsoft Excel to do the hypothesis testing. So this is one example that when you enter the data and you will receive this numerical solution from the MegaStat. And one as you can see in the last value, you see that this is the p-value, right, which is 0.3495, and it carry out for the one tail test, or the left tail test, because lower mean left, right? Okay, and you don't find the critical value here, right? Cannot find the critical value, so you see only the p-value. So if you want the significant level to be 0.1, so this is greater than, in this case, p-value is greater than the significant level. So you have to do not reject the null hypothesis, because based on the this, if the p-value is less than the significant level, you reject, but a while ago p-value is greater than, right? That's why we do not reject x0. So maybe it looks simpler to based on the p-value rather than the critical value, right? So it depends. You may decide on the critical value, significant level alpha, and then you have to compare it with the p-value generated by the software. Okay, by the software. Okay, this is the rule again. Okay, how to decide whether to reject the null hypothesis based on the p-value. Okay, here for the upper tail test, I refer to the right tail test. When you compute the test value, okay, this is the p-value, right, correspond to the right tail test, the area and the curve to the right of the test value. And for the lower tail test or the left tail test, the p-value is the area under the curve to the left of the computed z, right, or test value. And for the two-tail test, you have to combine this area, right, together. So in other words, it's given by this formula. This phi is the c-day function for the standard normal distribution. So it just summarizes this situation. Okay, so let's have a look at one example on how to use the p-value to decide on hypothesis testing. So in this example, a researcher wishes to test a claim that the average cost of tuition fee and fee, okay, it should be tuition fee at a 4-year public college is greater than this value. She selects a random sample of 36 4-year public college and finds that the mean to be this. Okay, actually this is the sample mean, okay, because it calculated based on this sample, right? And we know the population standard deviation is this. And the question is that is there evidence to support the claim at this significant level? And we require to use the p-value method. So to summarize, first of all, as the previous one, you have to state the hypothesis and identify the claim. So the initial value is this, right? And this is our claim. The researcher claimed that every tuition fee, every tuition fee of at a 4-year public college is greater than this value. It is the claim of the researcher. And then you have to compute the test value. Again, we use this formula for the test statistic, because our sample size is large, right? 36. So we don't need normality assumption. And then you, based on the value given, you found that the test value is 2.28. 2.228. You have to compute the p-value correspond to this, right? P-value. So the p-value in this case is you found z here, right? 2.28, and you want this area, okay? That will be the p-value. So how to do that with R? So to get the value with R, you have to I say, okay, I hope you can see this clearly. Z is 2.28, right? And we want the p-value. I denote it by p, okay, value. It equal to the p-norm. Okay, maybe d-norm. Okay, d-norm of z, right? D-norm of z. And by default, the lower dot tail, okay, lower dot tail is okay, lower dot tail equal to false. By default, false. So okay, let's try to run this. Oh, lower dot the d-norm p okay, we have to specify the mean. Okay, the mean equal to 0 and standard deviation equal to 1. Okay, I'm sorry, we forget to specify the mean and the standard deviation. Okay, and then so in this case, p-value is this. Okay. We found it to be 0.011. Okay, 0.011. Okay, here, it is this case, right? 0.011. By using the table, first of all, you have to find the area to the left of this z, right? But the p-value is the area to the right. Okay, to the right. So you have to subtract the area to the left from 1, right? And then you obtain the area to the right, which is 0.011, which is given, okay, by R with this code. Right? Okay, so I don't recommend using the table, but using R, right? So now you found that the p-value is 0.011, and then your significant level you choose beforehand to be 0.05. So in this case, your p-value is less than the significant level. When it's less than, you have to reject the null hypothesis, because based on the decision rule, when the p-value is less than the significant level, you have to reject H0, right? H0. So this is your decision, you have to reject it. Okay, here, okay, here, yeah. This is the your significant level 0.05, and this is the t-test, the test value, and the corresponding p-value is 0.0113, the area under the curve to the right of this test value. Okay, so how to summarize the result? Okay, there is enough, you can say that there is enough evidence to support the claim that the tuition fee at a 4-year public college is greater than this value. So you reject H0, mean that you support the alternative hypothesis H1, right? So it means the claim is supported by the data we collected, right? But again, it's not mean that your claim is true. It's just supported by the data, by the sample you collected. But make sure, please take note that if you change the p-value, okay, if you change the p-value, I'm sorry, if you change the significant level, the p-value is still the same, right? 0.0113, because the formula to come up with the z or the p-value is just solely related to the test value, and as you can see in the formula, it's not involved with the significant level alpha, right? Significant level just change the critical value, but it doesn't change the test value. So with this test value, we always have this p-value. So once you change the significant level to 0.01, in this case, the p-value is greater than the significant level. So you come up with a different decision, right? Because now the p-value is greater than the significant level of 0.01, you have to not reject the null hypothesis. Okay, as we note here, okay, if the researcher chosen alpha to be 0.01, the null hypothesis would not be rejected, right? Since the p-value is greater than the significant level. So it depends on how you choose the significant level. Sometimes with a certain significant level, you end up with rejecting the null hypothesis. But once you increase, decrease the significant level, you may end up with not rejecting the null hypothesis. That's why this is how we have some guideline for p-value. Okay, so if you compare the p-value with the significant level, okay, if you found that the p-value is less than 0.01, okay, reject the null hypothesis, and in this case the difference is highly significant, right? Because the p-value is very small. Okay, it's because the lowest significant level statistician always use is 0.01, right? And now we found that the p-value is less than this value, so in this case the difference is highly significant. But if the p-value is greater than this but lower than 0.05, in this case reject the null hypothesis, but the difference is significant, not highly significant. You still reject, but the way of your rejection is significant. If the p-value is greater than 0.05 but greater than less than 0.01, consider the consequence of type 1 error before rejecting the null hypothesis, right? Because in this case the error of the probability of error 1 is 10%, right? It's 10%. So you may reject or not, is up to you. But if you reject it, just consider the consequence of the type 1 error, because you may reject it while it is true, right? While it is true. And the probability that it is true is very high, 10%, right? 10%. And if a p-value is greater than 0.10, okay, do not reject it. Right? Do not reject the null hypothesis. And in this case, the difference is not significant. Not significant. So what is the difference here? Okay. The difference of the real value to the initial value, right? We mean that, right? The real value to the initial claim, right? This is u0 and not significant. The difference not significant mean you do not reject it, right? Do not reject the null hypothesis, mean that the real mean is can be something like this, right? Equal to the initial one. No, not significant difference. Okay, this is the code. Okay, for the R code for when we consider p-value instead of the critical value, right? So I give this example because this example you end up with rejecting the null hypothesis, right? So I want to test with R whether it's generate the same result. Okay, so I name this file which is C test with critical value. I already sent you, right? I already sent you. So in this case, just run this. Okay, control all and then run it, and then okay, there is not enough evidence to reject the null hypothesis, which is the same as the result here, right? Okay, I don't know which example is this, but the code is for the p-value. Okay, this is example. You can try this by yourself because we have several examples here in the slide. I will send you again the slide because a while ago I have I noticed some. Okay, so usually this is the problem of like you come up with hypothesis about something. For example, the population mean. Okay, you conjecture that it equal to a certain value, and then you will try to find some evidence to support your claim, right, about something, for example, about the population mean. So you're trying to find evidence to support your claim. The evidence in this case is the data you collected, right? So usually there are two conclusions for hypothesis testing. You may end up rejecting the null hypothesis, or do not reject the null hypothesis. Okay, one of the two conclusions, one of the two possibility. But once you know that, once you conclude that the null hypothesis should be rejected, it does not mean your conclusion is true, right? It doesn't mean like that, but it means that based on your data, you have enough evidence to say so, right? To conclude that. But in reality, your conclusion may be false. Okay, so that is refer to the error of the test, right? Okay. So for example, so far we have something like this. Okay, you may say, okay, the mu is different from this, right? The mean, okay, the mean is different from 24,672 US dollar. Okay, what is that mean? Okay, the average cost of rehabilitation of stroke victims. Okay, so you claim that in average the cost of rehabilitation for the stroke victim is different from this. That is your claim. And then in order to support your claim, you may like collect some data, okay? Because your claim is about the population, right? Any rehabilitation must be included, okay? And if you know that, you can compute the real mean, the real average value, but in practice it's impossible because you not always approach the population data. That's why in practice you have just resort to collecting a sample, right? Selecting a sample. So in this case, we're trying to find a sample to support whether our claim should be rejected or is right or not, right? So the conclusion may be end up with whether you have this or this, right? But again, since nu is unknown, so when you come up with the conclusion, you cannot say it is true or not, but at least you can just say you have enough information to conclude or to say so, right? To say so. But it may happen that your conclusion is incorrect, right? Incorrect. That's why in hypothesis testing, there are two possibility of error. Okay, we have type 1 error and type 2 error. Type 1 error is, okay, let's review a little bit here. Okay, this is just your claim, right? And claim. Okay, so we do, have two kind of hypothesis, H0, and we call this null hypothesis, and H1 is the alternative hypothesis. So you may come up with like reject X0, and in that case, okay, just like look at this, maybe it's more convenient to explain why using this. Okay, suppose that this is one hypothesis, okay, and this is the null, I'm sorry, the alternative hypothesis. So as you can see, we have two kind of error. Okay. The type 1 error is that you reject the null hypothesis while it is true, right? It means that in reality, H0 is true, but based on your data collected, you conclude that H0 is not true, or you reject it, right? You reject it. So that is one possible error, right? Yes. So here, suppose that the null hypothesis is true, it means that you are not pregnant, and then you come up with rejection it, right? Reject it, right? So you reject this, it means that you are not pregnant, it means that you are pregnant. But of course, this is your claim, or the original claim, and in reality, this guy is not pregnant. It's true because he is a male, right? But you come up with a conclusion that this guy is pregnant. That is possible error. And another error is that you do not reject null zero, null hypothesis, when it is false. Okay, when it is false. So here, if null hypothesis is false, it means that the in reality the guy is pregnant, right? The guy is pregnant, but you do not reject it, right? You do not reject it. It means that you say that you are not pregnant, but in reality it is true that this woman is pregnant, but you come up with conclusion that you are not pregnant. So this is the two possible error in hypothesis testing. Okay, and so far we have deal with hypothesis related to this population mean, right? You just come up with a claim, and then you're trying to find evidence to support your claim, right? Okay, and eventually you come up with two possibilities in your conclusion, right? Whether the null hypothesis should be rejected. Okay, and in this lecture, we move to another thing. Okay, we move to another thing. It is about the test with a population proportion. Okay, but I will not consider this. I just move to the test for a variance or standard deviation. Okay, this is makes sense because in general, the two parameters, the population mean and the population variance are unknown, right? So you may also want to test about the variance, right? Originally you test with the mean, now just move to another step. You want also to test the variance. You come up with a claim with related to the variance, and then you're trying to collect data, and based on that data you may come up with conclusion whether your claim is true or not, right? Okay, but in this case we have to assume that the population is normally distributed, right? Okay, I'm sorry, I'm trying to erase this, but I don't have time. That's why this is just a typo. Okay, there should be no this phrase. Okay, so we just assume that we just select a sample of science from a population whose distribution is normal, right? Yes, we assume that the population is normally distributed, and then the two parameters are unknown, and then you try to come up with some hypotheses related to the sigma square, the variance. Okay, the null hypothesis could be like, you may say, okay, the population variance equal to a certain value. Okay, this is our initial hypothesis, right? It means that the variance is equal to a certain value. This is mean a certain value. You can denote this by any other letter, okay? But make sure that this is a certain value, right? It means that the null hypothesis claims the variance equal to a certain value. And the test hypothesis, the statistics, the test statistic in this test a little bit different from the mean test. So you have to work with this kind of test, right? You have to work with the sample variance x square, and this is the n-1, n is the sample size, okay, and sigma 0 square is the certain value, okay? So you have to test, your test statistic is this, right? And we call it chi-square because, as you know, when you study confidence interval related to the variance, it related to the chi-square distribution. When we're working with confidence interval with the mean, we're working with the standard normal distribution or the t distribution. But when we move to the confidence interval for the standard deviation as well as the variance, we will involve with a different distribution called the chi-square, right? And at that time we denote it by this letter. Actually, this is chi-square. This is the Greek letter called chi-square. So this is three possibility of the alternative hypothesis. Okay, this is the original hypothesis. I mean the initial hypothesis. So you may have the one-tail test. Okay, one-tail test. You may have another hypothesis as that the true value of the variance is strictly greater than this certain value, or it's strictly less than, right? These two tests is the one-tail test, right? Or you may have a two-tail test, like the null hypothesis in this case is that the variance is different from the original value. And this is the corresponding rejection region for the three tests. Okay, so in this case, the rejection region is you have to look at any value that greater than this, right? Okay, you already see something like this when we working in the confidence interval. At that time, we call the right. Okay, just a moment. Here, okay, here we have Okay, x. Okay, x chi-square left and chi-square right. That is what it means, right? By that, because like t distribution, chi-square distribution is characterized by the degree of freedom, right? The degree of freedom. And unlike the t test, the t distribution, chi-square is not symmetric, right? This is one example of the chi-square curve, and then you have to also working with the critical value, right? You come up with a critical value. You may say chi-square right correspond to like this value, right? This means that this is the point at which the area under the curve to the right is alpha over 2. So and this is the left when you think of the area to the left. This is when you think of to the right. But this is a different notation. Okay, a different notation. Okay, this is just the same thing, right? N-1 is the degree of freedom of the chi-square test, and this alpha, okay, this alpha is the what is mean? Okay, it is the significant level, right? Significant level. So when you have only this is the right test or the upper test, right? Upper tail test. So what does it mean? This means this one, right? Instead of call it chi-square right, in this case I just call it chi-square alpha n-1. N is the degree of freedom, because you may have a lot of chi-square curve when you just specify the degree of freedom. This is several chi-square curve correspond to 4 different degree of freedom, right? And the way we define the critical value is in this way. Okay, chi-square right here in this case mean this one. It means that this is the point that the area to the right is alpha, right? It's alpha, and you have to specify the degree of freedom n-1. And for this, this is actually the chi-square left, right? Because for example, if I say that this is alpha, this must be chi-square alpha, right? If this area is alpha, this is chi-square alpha. But in this figure, this area is alpha over 2. So this is chi-square alpha over 2, right? So to come up with this value, you just take alpha to be, okay, 1 minus alpha. Why? Because if this is alpha, 1 minus alpha means the area here is 1 minus alpha, and the area here is just only alpha. So we mean, okay, this is just the right, the left the left chi left, right? I mean the left chi-square value. And this is the case when we think of 2 tail, right? Or both tail. So when you specify the significant level alpha, you have to set the area to the left and to the right alpha over 2, right? So what is the corresponding chi-square right? It is this one, right? It is this one, chi-square alpha over 2. This is exactly chi-square right, and the chi-square left in this case is exactly this one, right? Because when you want it to be here, the chi-square, this area must be 1 minus alpha over 2 to the right, right? To the right. area to the right is 1 minus alpha over 2. Okay, this right area is 1 minus alpha, but when you plus this more, you're gonna have 1 minus alpha over 2. That's why here it is chi-square 1 minus alpha over 2, and you have to specify the same the same degree of freedom, right? If you look at this, everything just quite similar to the case of test for the mean, except that we switch from we switch from the standard normal distribution or the t distribution to the chi-square distribution, right? To the chi-square distribution, and everything just works in the same way. Okay, this is nothing but the critical value, right? This is the critical value here. Chi-square right or chi-square left, we mention it as the critical value, right? Just like for the z, for the case of standard normal curve or the t. Okay, where is that? Just okay, here. Okay, this is correspond to the standard normal curve, okay, and it is the z curve, and the distribution is z, right? Standard normal, and the corresponding critical value we denote it by z alpha or z alpha over 2. And similarly, for the t curve or the t distribution, the critical value we denote it by t alpha. Alpha here, it just means the same way as the significant level, but t here you have to index it by two values, the significant level alpha and the nu, which is the degree of freedom. And similarly, in the case of chi-square, everything just works the same. Okay, everything just works the same. Okay, this is a chi-square curve, right? Because the distribution is the chi-square is chi-square, right? And this is the corresponding critical value. But since the curve is no longer symmetric, that's why you have to say two different things, right? Chi-square right and chi-square left when it's come up with the two-tail test. And it is nothing but here, right? Here. Okay, so let's move to the point. The point is that an instructor wishes to example. This is example. An instructor wishes to see whether a variation in score of a. Okay, maybe it's better to have an example here. Okay, I'm sorry if it is raining now. That's why you may hear some noise from the outside. Okay. Okay, so this is one example of the hypothesis testing for variance. Okay, so actual test. A psychologist wishes to see if the variance in IQ of 10 of her counseling patients is less than the variance of the population, which is this. Okay, the variance of the IQ of her patient is okay. Please Please let me know if you can hear me clearly.
Yeah, I can hear you clearly, Professor.
Okay, because
Yes,
I
sir.
read because I myself just hear the noise very noisy, and okay, it's okay if you can see clearly. If you can hear clearly, okay. So this is how we can use the chi-square test. Okay, uh, so the variant of the IQ of her 10 patient was, okay, this is the variant. Actually, this is the sample variance. Okay, this is actually the sample variant because this is based on this sample. You select a sample of 10 patients, right? Yes. Your claim is we're trying to compare the variant of the IQ of the patient selected to the variant of the population. So we know the population variant is this. Okay. So in this case, you have to state this hypothesis that this is your null hypothesis is okay, original claim. Okay. And your claim, this psychologist claim is that the variance is less than this, right? It's less than this. So first of all, we have to find the critical value. Okay, the critical value. Since this is the left tail test, why it is left tail? Because here you have to. It depends on your alternative hypothesis, right? If the sigma square is greater than a certain value, it is considered as the right tail test or the upper tail test. And when it is less than certain value, it is the left tail test or the lower tail test. And if it is different from a certain value, it's considered as the two tail test. We classify this exactly the same as the case of the population mean test, right? But since the alternative in this case is less than a certain value, it is the left tail test. And we want the significant level of 0.05, which means that we want the, okay, if you think of confidence interval, the confidence level is 95%, right? 95%, which corresponds to the significant level of 0.05. Okay, so so when your alpha is 0.5, 1 minus alpha is 0.95. And the degree of freedom in this case equal to the total, the sample size minus 1. Sample size in our case is 10 because we select a patient of 10, right? So the degree of freedom in this case is 9. And the critical value is this. Okay, why is that? Because here we want the left. We want the left test, okay, left hand test, this one. Then this is the critical value, okay. Chi-square 1 minus alpha, right? Because we want actually we want this area, okay. We want this area to be alpha, okay, to the left, right? This area to be alpha, and then the area to the right is 1 minus alpha. That's why in this case we need 1 minus alpha is 0.05, and then this is actually z chi-square, okay, chi-square 0.959, right? because 1 minus alpha is 0.95 and the degree of freedom in this case is 9, right? Okay. And then this is your test value. Okay, your test value. You have to compute this n minus 1 times sample variance divided by the second value. That's why you have to compute this. Okay, n minus 1, 10 minus 1, and s square. We know that it is given. Okay, it is given. Oh, I'm sorry. Here it is given. It is given, and divided by the original value, right? The original value, and then you come up with this. And then how to make conclusion? Okay, here you can make. You can see the maybe it's better look. You want this area to be 0.05, right? You want this area to be 0.05, and then you want to identify this point, right? So how to get this value? You have to look at the chi-square table. But the chi-square table just gives you the area to the right. So if you want this area to be 0.05, the area to the right must be 0.95, right? So that's why we have to compute this 0.05 and specify the degree of freedom. You can come up with this critical value. It's mean get this value, right? And then you have to compute the test value. In this case is 8.24. And how you decide? Okay, how you decide? For the left tail test, okay, because our problem is left tail test. The corresponding rejection region is this. You have to compute the test value. If it's less than this critical value, it means that you have to reject, right, the null hypothesis. But if, in contrast, if it's greater than this value, you have to do not reject, right? Do not reject. So that's why when this is the critical value and this is the test value, and as you can see, this is the rejection region, but now the value is outside the rejection region. That's why you do not reject, right? Do not reject the null hypothesis. Okay? Do not reject the null hypothesis because our test value fall outside the rejection region. This is the rejection region. If the value is less than this, you have to reject the null hypothesis. But in our case, the test value is 8.04. It is to the left of this value, which is outside the rejection region. That's why you have to come up with this conclusion. Do not reject the null hypothesis. And how can you say? How can you summarize your result? There is not enough evidence to support the claim that the variance of her 10 patients is less than this. There is no enough evidence to reject this null hypothesis, or equivalently, there is no enough evidence to support this. Right? Okay, again, we come up with a conclusion of do not reject the null hypothesis. It means that there is no enough evidence to reject this, or there is no enough evidence to support this, right? There's no enough evidence to support this. So we don't have enough evidence to support the claim, right? The claim of what? The claim of alternative hypothesis. Okay, this is another example. Okay, it's about outpatient surgery. Okay, a hospital And Mr. believes that the standard deviation of the number of people using outpatient surgery per day is greater than 8, right? The standard deviation is greater than 8. A random sample of 15 days is selected and the data is shown. Okay. What is that? Number of people using outpatient surgery. Okay, outpatient surgery chia ca vẹt cắt ở trên cái ở sầm mẹ thì chẳng miền này tha quạt đập hẻm ngày mò sặc xá ngày. Okay, one day there are 25 outpatient. Okay, using there are 25 patients who use the outpatient surgery in this specific day, and there are 30 patients using the service in another day, and so on. And then we want to come up with a significant level of 0.10. So we want to know if there is enough evidence to support the administrator claim. How he claim? He claimed that the standard deviation of the number of people using the outpatient surgery per day is greater than this, right? So you may come up with this hypothesis and identify the claim, right? So this is the null hypothesis. It compare with 8, right? So this is the certain value of standard deviation, and because the claim is that it's greater than. Okay, this is the claim of the administrator. So in this case, the claim of the administrator is alternative hypothesis. So since the standard deviation is given, it should be squared to get the variance. Okay, so first of all, again, we have to compute the critical value correspond to this significant level, right? We want a significant level of 0.10, and you also have to specify the degree of freedom. So the degree of freedom is 14 because we select a data of 15 days, right? So the degree of freedom in this case is 14, and the test is right test or upper test. I'm sorry, right tail test or upper tail test, because the alternative hypothesis is greater than, right? It's greater than. So in this case, you come up with this critical value from the table. Okay, we want this area to be 0.10. So the critical value in this case is 21.064. Okay, here. And how to come up with this value? You have to look at the chi-square table, because I already tell you how to do that when we working on confidence interval for the variance as well as for the standard deviation. And another way of come up with this value is using R, right? You have to use the right command to come up with this value. And again, you have to compute the test value. Okay, this is still our test value. Even we come up with a test related to the standard deviation, not the variance, but the test value still working with the variance. But again, since the standard deviation is given, you just square it, you come up with the variance. That's why everything is realized here. So just replace. Okay, n is 15 because we select a sample of 15. And s square is 11.2 square. Okay, how to come up with 11.2? Because this is a sample, if you compute the sample variance, you will obtain this, right? 11.2 square. This is the sample standard deviation, 11.2, based on this data. Okay. and 64 is a square of 8, right? Because the sigma is originally claimed to be 8, right? So this is a test value, and in this case the test value is to the right of the critical value, and this area is the rejection area, and our test value based on the data, based on the sample, it is inside the rejection region. That's why that the data suggests us to reject the null hypothesis, right? So this, the decision is to reject the null hypothesis, right? Because the test value is greater than the critical value, right? Or in other words, it's fall inside uh, the, the rejection region or the critical region, because this region is called critical region or rejection region, just the same thing, synonym. And the result is there is enough evidence to reject null hypothesis, or in other words, there is enough evidence to support the alternative hypothesis, which is the claim of the administrator, right? So that's why we come up with there's enough evidence to support the claim that the standard deviation is greater than 8, right? Greater than 8. Okay, and this is an example of a two-tailed test. Okay, we want to think it's related to the nicotine content of cigarettes. Okay, a cigarette manufacturer wishes to test the claim that the variant of the nicotine content in its cigarette is this value. Okay. Nicotine content is measured in milligrams and assume that it's normally distributed. So the a random sample of 20 cigarettes has been selected, and we measure that the standard deviation is 1 milligram. Right? This is the sample standard deviation because this value is calculated from this sample. Okay, this sample. And we want the significant level to be 0.05. So the question is that, is there enough evidence to reject the manufacturer claim? Okay. We claim that the nicotine content just only this, right? So based on because maybe according to the law they have to restrict a certain variance, right, of the nicotine inside cigarettes. So in order to see whether this kind of cigarette observe the law, we have to test this value. So based on what is told, you have to state the hypothesis and identify the claim. Okay, this is a claim because it claimed that the variant is, okay, this value. And this is the alternative, right? The alternative. So again, in this case, because the alternative is different, it is the two-tailed test, right? Two-tailed test. Okay, so you have to set 0 point, okay, alpha is 0.05, so you have to divide alpha into 2, 0, 0, 25, and another 0, 0, 25 to the left, right? So what you have to do is to compute this critical value corresponding to this. Okay, so again, using this critical value and this degree of freedom of 19, because we have a sample of 20 cigarettes, the sample size 20, the degree of freedom in this case is 19. And using this significant level for the two-tailed test, we come up with this critical value, right? So in this case, the rejection region is to this or this, right? So you have to compute the test value. Okay, you have to compute the test value using the same test statistic because everything is given here, right? And then you come up with a test value of 29.5. And again, where is 29? 29 is between this critical value. So it's outside the critical region or the rejection region. If our test value is inside this or inside this region, we have to reject the null hypothesis. But it's outside. It's outside. Do not reject. So the conclusion is that do not reject the null hypothesis, since the test value just fall between the critical value, or in other words, it's stay outside the rejection region. Right? So this is how we conclude. Right? There is not enough evidence to reject the manufacturer claim that the variance of the nicotine content of the cigarette is equal to this value. Okay, and this is the finish what I planned for you. Actually, you may ask like, okay, the way to conclude the hypothesis testing can be looked at or compare the test value with the critical value, right? As you have seen so far. And another way to come up with the conclusion, you may compute the p-value instead, right? And then compare the p-value to the critical value. That is another way of doing that. But since you have seen this in the case of hypothesis testing for the mean, it works just exactly the same way for the hypothesis test for hypothesis testing for the variance as well as the standard deviation. So I think it's good enough to finish here. Okay, to finish here. So please let me know if you have any question.